This is Nicholas Vinan from Silicon Chip Publications, and today I wanted to talk about our new USB power monitor. Now, this article you see on the screen is not the new one. In fact, this is from December 2012. This was our first USB power monitor, and I wanted to talk about this first because it's an interesting comparison. So this device has a USB Type A plug-in socket, and you can see here it's measuring the power drawn by this flash drive at 334 milliwatts. And it shows the readings on this 4-character LCD screen. It can show voltage, current, power, and I believe energy as well. And here's the circuit. You can see it's a pretty simple circuit, and that's because USB 2 and 3 were pretty simple, really. The voltage was basically fixed at around 5 volts. It does measure the voltage. It does it in a somewhat interesting way, which is that the 5-volt supply powers this chip IC1, and it has an internal fixed reference voltage that it measures as a ratio with its power supply voltage. So it can figure out the 5-volt supply voltage without having to, well, it essentially is measuring it through its supply rails. But the current measurement is a bit more complicated. The current flows from the plug to the socket through this 50 milliohm shunt resistor, which has special Kelvin connections to make it more accurate. And then that connects to an INA 282 instrumentation amplifier, which amplifies the difference between the two ends of the resistor by a fixed amount. I think it's 50 times, something like that. It's offset by a reference voltage, and then it's fed to the microcontroller to measure and ultimately display. It's also further amplified by a factor of 10 by this op-amp IC3B. That gives it more accurate readings at low currents because it's not so limited by the resolution of the analog to digital converter in this microcontroller. So all in all, a pretty simple design. You can see actually a lot of it is really just the lines to drive the LCD screen. And that was chosen partly because it draws very little power and it can be driven directly from this chip. But a lot has changed since the end of 2012. And now we have the option of fairly power efficient and bright graphical OLED screens, and they don't need so many connections from the microcontroller. So now we have this new USB-C power monitor published in the August and September 2025 issues. It needs to do a lot more than that early one because USB can now do a lot more. So for example, it's not just stuck at 5 volts now. It can ramp up to, I think, as high as 40 volts. So the device needs to be able to handle higher voltages, higher currents, and the more complex signaling used by USB 4 and compatible protocols. And it also uses USB-C connectors, partly because that's a new standard, and partly because the new USB power delivery requires that the extra contacts in the USB-C. And you can see down here in the article, one of the first things we do is show the USB-C connector. The original USB used D plus, D minus, V bus and ground. Now we have CC1 and CC2 for configuration channels, sideband channels, 4 extra differential pairs plus extra grounds and so on. So it's quite a bit more complicated. And if you have a look at the circuit shown here, well, it doesn't look that much more complicated. Of course, a lot of it is simplified because of this display module only requiring 3 pins to drive it. We've connected VCC to a pin on the microcontroller so we can switch it off. The display draws little enough current that you can just supply it straight from a digital output. Drive it high and the screen is on, drive it low and the screen is off. And then we just need these 2 pins to control what's on the screen. So that's all nice and simple. The power supply is quite a bit more complicated, partly because we now have a battery. The reason for that is partly because the circuit consumes a bit more power now, and we don't want to draw it from the USB because we'd be interfering with the measurements. And partly because if that's right on the limit of what it can deliver, this could push it over. So instead, we have a separate USB socket that's used to charge this battery using this chip. When it's charging, power is supplied directly from this socket through this diode. Otherwise, it comes from this battery into this boost regulator that produces the 5 volts to run the circuit. So power here is completely independent of the actual test sockets. You can see we now have 3 shunt resistors. The main shunt is 15 milliohms, so it's about a third the value of the one in the old tester, and that's because it would burn up if we were to drive several amps through it, which we now need to be able to do, which means a bit more gain in the measurement circuitry. But we also have shunts on the CC1 and CC2 pins, and that's essentially so we can tell which end is supplying power and which end is sinking the power, because USB-C is symmetrical now, so it could flow in either direction. And in fact, that means we also have to measure current flowing in either direction. So this circuit can do that now. We're using the same instrumentation amplifier to do the actual measurement across the shunt. And similarly, we also have this extra amplifier to provide the higher resolution mode. So this part of the circuit is pretty similar to the old one. But there's a bit more going on here because it has to handle higher voltages and currents and so on. We do directly measure the voltage now. We need to be able to do that because it's no longer directly powering the chip. But otherwise, it's a pretty straightforward circuit where we measure the current, measure the voltage, we display them on the screen. Of course, now that it's a graphical screen, but we do pretty much the same thing where we measure the current, measure the voltage. We can show either of those, or if we multiply them in the software, we can show the power, and we can also accumulate that over time to show energy. And of course, now that it's a graphical screen, we can show much more detail. It's not just 4 digits. We can show the voltage and current at the same time. We can show the energy and the power. We have a timer that you can reset so you can accumulate energy over a fixed period. So it's a very handy little instrument now. You could do things like see how fast your phone is charging, how many watts it's drawing by connecting this in line. You can also see whether it's negotiating a higher voltage. You can see the current, all sorts of stuff. So it's a much nicer device. It's a little bit more complicated in terms of the assembly, but it's still not too bad. There's actually 2 boards now. So the easiest way to do this, we thought, was this board really is just for the plug-in socket and the shunts. And then it just has these 7 connections that go via ribbon. If we look at the part 2, it shows more of the construction. So here's the main board that has the microcontroller, the screen, and the other circuitry. It's a little bit more complicated, but not too much. But one of the nice things about it is everything is surface mounted on this side of the board, which means the other side of the board is actually the device's front panel. You can see it's hinged open here, and how the ribbon connects this board with the connectors to the board with the circuitry, and there's this battery in between that's used to power it. And I believe that will last at least a few hours of use because the circuit doesn't draw all that much current. Now, of course, a lot of the complexity of a device like this is in the software. You can download the software, the source code is available. But we do show some of the different screens. There's the main screen showing the voltage and current and the power and so on. You can do calibration. It's not necessary, but you can get slightly better accuracy if you actually use a multimeter to compare the measurements and adjust them. You can change the screen brightness, set whether the energy is shown in watt hours or joules. You can put it into sleep mode, which is actually automatic. If you don't use it for a while, it goes into sleep mode to save power. And the rest is just calibration. There's also some information here on how we're monitoring what USB is doing. It's a little bit tricky because we're trying to intercept these communications, but we can do that. And the rest of the article is basically just some hints on, or here's showing how you can test it. So these things act as loads. You can buy these little PD trigger boards, which are quite handy, that let you request a certain voltage from the USB source. And that can be used for testing. And then we also have a little bit of information on the assembly, just cutting out the notches in the box, which is pretty straightforward. There are only 3 of them. And that's one of the nice things about using the PCB as the lid. We don't need to cut a hole for the screen, for the buttons, for the charge LED. It's all just, the PCB comes with the holes made, so it's all ready to go, and you just screw it into the case. It replaces the lid that comes with it. So a neat little package, a very handy unit. This article series was published in the August and September 2025 issues. The August issue has part 1, which covers the circuit description and has the parts list, so that you don't have to buy all these parts separately. We also have a kit. Kit comes with pretty much everything listed here except for the case and the battery. So it has the 2 circuit boards, the ribbon cable, all the parts that mount on the boards and so on, the program chip. So it's pretty straightforward to get put together, and you just need to get the case and the battery, and it's a complete unit. And then the September issue has the construction details, which includes the overlay diagrams that show which parts go where on the PCBs, and some testing instructions. As I mentioned, case preparation, calibrating it, using it, etc. So a very nice little project, I think. You can buy things like this. I don't think the ones that you can buy are necessarily as comprehensive as ours. And of course, it's always nice to know how it works. And in fact, because we provide the source code, if people want to modify this to do different things, it should be quite straightforward. The microchip software for compiling the code is free. So you can download the code, you can download the software, compile it, upload it to the chip, and make your own version if you want to. I hope you found that interesting. Thank you very much for listening.